Hello and welcome. Grab a hot drink or something equally nice and take a seat. Today we begin a series of videos exploring, a certain topic, and you'll see what that topic is. And let's talk about where this exploration all started. It started when I first learned a technique for solving a certain kind of equations. So this concerns sequences, and I'm going to first define what a sequence is. A sequence, which looks something like this, un, where n is greater or equal to 0, is an infinite sequence of numbers that depend, where each term looks like what is inside of the brackets. So this un is going to look like u0, u1, u2, u3, and so on. And specifically, we're interested in the Fibonacci sequence. The Fibonacci sequence is the sequence where each term is the sum of the previous two terms. Or symbolically, a Fibonacci sequence is a sequence such that the nth term un is equal to the n minus 1th term plus the n minus 2nd term. And also we have some initial conditions telling us where the sequence starts. u0 is equal to 0 and u1 is equal to 1. So if we were to write out this sequence in the form above, first we would have u0, which is 0, followed by u1, which is 1, followed by u2, which is given by this rule, that the second term is equal to the first term plus the 0th term. So the second term is 0 plus 1, which is 1. And the next term is 1 plus 1, which is 2. The next term, 1 plus 2, which is 3, and so on, infinitely. So the technique I was talking about, it answers the question, is there a nice formula for the nth term a nice formula as in one that isn't recursive like this one, where we potentially have to calculate all the terms before the nth term to know what it is. And, well, this was what I learned. First, we suppose that we have a geometric sequence that satisfies this recurrence relation. So suppose that for some lambda constant, un is equal to lambda to the n. And let's see what possible values lambda can take. Well, we know that un must be equal to un minus 1 plus un minus 2. So substituting in, we get that lambda to the n must be equal to lambda to the n minus 1 plus lambda to the n minus 2. And here, assuming lambda is not 0, so I better add that, not equal to 0, we could divide through by lambda to the n minus 1 throughout this equation, which gives us lambda squared equals lambda plus 1. Well, this is a quadratic equation, so we use whatever method we like, such as the quadratic formula, to solve it. And we end up with two values of lambda. Lambda equals 1 plus the square root of 5 over 2, or 1 minus the square root of 5 over 2. And I'm going to call these two lambda 1 and lambda 2, respectively. I just noticed that I don't have a hot drink. I hope that's okay. So that's step one. So we've said that we have these two geometric sequences, or these two powers of a whole number that can give us, that satisfy this equation. But we notice that these two, lambda 1 to the n and lambda 2 to the n, they don't fit our initial conditions, because if un were lambda 1 to the n, then what happens is our first term is lambda 1 to the 0, which is 1. Our second term is lambda 1. Our third term is lambda 1 squared, and so on. While we get a similar thing for un equals lambda 2 to the n. We have 1 lambda 2 to the n, lambda 2 squared, and so on, which not satisfy initial conditions. Okay, so now how do we satisfy the initial conditions? Our method tells us that our actual un is equal to some constant a times lambda 1 to the n plus some constant b times lambda 2 to the n. So I'm going to say that a, b are constants, depend on initial conditions, ICs. Okay, so let's try what happens here. So we consider n equals 1 and n equals 0, because those are our two initial conditions. We get that u0 is equal to 0, which is equal to a times lambda 1 to the 0 plus b times lambda 2 to the 0. And we get that u1 is equal to 1, which is equal to a times lambda 1 to the 1 plus b times lambda 2 to the 1. So here we have two equations and two systems. And we could show with some, with many ways, kind of all linear algebra-y, that this equation is going to work for any initial conditions, u0 and u1. And we could also come up with some conditions for when we're going to get a unique solution for a and b, given our lambda 1 and lambda 2. So this raises a whole host of questions, like how are these coefficients a and b related to the initial conditions? Or is there a case where lambda 1 and lambda 2 are such that we get no solution for a particular set of initial conditions? Well, these are interesting questions that I'm not really going to look at. Except to start you off, I'm going to rewrite, if you're interested, I'm going to rewrite this as a column vector matrix equation. I'm saying that u0 u1 is equal to lambda 1 to the 0, lambda 2 to the 0, lambda 1 to the 1, lambda 2 to the 1 as a matrix multiplied by a and b. So there being a unique a and b corresponding to a set of initial conditions is exactly inverting a matrix. Okay, so this method raises many questions as to why this works. And I'm going to point out two in particular that bothered me and really piqued my curiosity. So the first question is, why do we consider geometric sequences to be our solutions, to build our solutions? To remind you, this is the bit when we said suppose un is equal to lambda to the n for some lambda. And the second question is, why do we consider a linear combination of the geometric sequences we get. How come we didn't consider some other method of combining the two solutions? Like, I don't know, maybe multiplying them together or something like that. And why is it that we didn't think about, how is it that we can convince ourselves that actually a linear combination of our two geometric sequence solutions always give us work for every single initial condition? It could be that it seems quite reasonable that maybe this linear combination only covers part of the solutions. Although it gives us a bunch of solutions, it might not give us everything. And for the first question, why is it that we didn't think about arithmetic sequences, or maybe some fancier kind of exponential where we have like n times lambda to the n? Or why didn't we consider trigonometric functions as our building blocks? Or maybe why didn't we use a kind of power series or something? Why geometric sequences? So this method, although it was interesting to learn at first, it left me just kind of in awe and confused. What is going on? We could do better with our understanding. So the Fibonacci sequence, and actually its whole family of sequences, are what's called linear difference equations. By whole family, I mean sequences where the nth term are a linear combination of some previous terms. So it could be like the Fibonacci sequence, where we have one term is the sum of the previous two terms. Or it could be something like one term is the sum of the previous term, the term before that, the term before that, 2 times the term before that, -5 times the term before that, 10 times the term before that. So it could get very long. And to solve each of those, this technique that I first learned tells us that we could suppose a geometric sequence satisfies the equation, solve this polynomial, and then write the solution as a linear combination of these geometric sequences. In this series, we're going to follow those two questions that I asked. Why geometric sequences and why linear combinations? And we're going to keep on following this hierarchy of topics, ideas, and more questions that come from them, until we get to a place where this technique seems perfectly natural, and that the theory underneath it we understand and is something that is really beautiful. And here I've drawn an order diagram of the different questions that we're going to follow and the topics that they lead to. So you could see that we're starting at the bottom, and there's this whole cloud of topics that are shrouded in mist right now. In this video, we're going to first follow the question to the left, which is, how come we're supposing that we're using a geometric sequence? Let's build some intuition for that. Consider the Fibonacci sequence. 0, 1, 1, 2, 3, 5, 8, 13, and so on. Now this sequence, we could tell that it's going to grow, and it's going to grow to infinity. But how fast is it going to grow? Well, the two kinds of sequences that people first learn about, or seem the most natural to think about, are arithmetic and geometric sequences. Arithmetic sequences have the property that there's a constant difference between successive terms. And we'll show that that's not the case for the Fibonacci sequence. So consider the difference between 0 and 1, that's 1. The difference between 1 and 1, that's 0. The difference between 1 and 2, that's 1. The difference between 2 and 3, that's 1. The difference between 3 and 5, that's 2. The difference between 5 and 8, that's 3. And you can see that actually the differences are another copy of the Fibonacci sequence, but transposed one term or so backwards, and that the difference goes to infinity, so that it cannot be arithmetic. And we could prove that actually we do have an exact copy of the Fibonacci sequence from the Fibonacci sequence's recurrence relation. We have this recurrence relation. If we subtract un minus 1 from both sides, then on the left-hand side, what we get is the successive differences between the terms. And you can see that the successive differences between the terms is exactly a copy of the Fibonacci sequence, but 2 terms backwards, which is what we observed. Okay, so could it be geometric then? The criterion for a sequence to be geometric is that the ratio between successive terms is a constant. For example, the geometric sequence 1, 4, 16, 64, 256, and so on have their common ratio, the ratio between successive terms being 4. So let's check the ratio between successive terms for the Fibonacci sequence. You can see I've filled up this table, and that the ratio of successive terms aren't constant, so our sequence isn't geometric, but there seems to be a pattern for this ratio. For that, let's plot the ratios on a number line. So you could see that as we increase the terms that we're considering, as we consider the ratio between terms which are farther and farther down the Fibonacci sequence, on our plot we see that there seems to be some constant ratio that this ratio is approaching, that is somewhere between 1.6 and 1.7. And although it doesn't seem to quite reach this invisible number, this seems to suggest that as we consider larger and larger terms in the Fibonacci sequence, terms farther and farther down the line, the Fibonacci sequence is going to tend towards a geometric sequence. The ratio between successive terms is tending towards a constant. As in, if we look far enough down, then we're essentially looking at a geometric sequence. Now, this isn't a proof, because we haven't actually shown that these ratios converge towards anything, but it does give us some hint. A geometric sequence can satisfy this Fibonacci relation. Now this leaves us the question, how can we be sure that geometric sequences are actually what's showing up here? And was there a way to come up with this geometric sequence idea without considering this pattern spotting process of plotting some numbers and then having a reasonable guess? Well, for that, it's actually hard to tackle it directly from where we are right now. Instead, we'll have to go up the right path of our order diagram. Have a break and maybe grab a refill of your hot drink. Come back for the next videos.